final frequency response. So what we're going to do today is to basically review the single stage. In the textbook, of course, there's more complicated circuit, frequency response on more complicated circuit. But for this class, and with other class provided by Professor Wang, we decided to just focus on single stage amplifiers. So the last topic is that we're going to talk about frequency response on single stage amplifier. So that is to say, we're going to focus on, of course, first is common emitter or common source, and talk about common base and common gate. And then lastly, we're going to talk about the follower circuits. Okay? So in discussion of the frequency response, there's basically two regions. One is that we're going to, of course, talk about the impact of so there are basically two regimes at low frequency. Typically is the coupling capacitance. There's coupling and what we call the bypass capacitance. These are typically external capacitance. You deliberately added external cap, meaning that it's added by designer to fulfill certain functions. So for low frequency, typically the impact of coupling or bypass capacitance. These are typically used to settle or to set proper DC biasing conditions. So these are coupling capacitance and bypass capacitance. We call it CC or CB. These are for setting, typically used for setting proper DC levels. And for the high frequency part, in high, we call the high frequency regime. So we separate into the high frequency and low frequency the discussion. In high frequency regime, what happened is that you need to consider parasitic. That means that it's internal inside transistors. So come with transistor. Once you build a transistor, these are the things that come within the transistors. These are the capacitance we already talked about inside, which is mostly for BJT will be C pi, C pi, C mu junction capacitance. These are typically the capacitance we consider for BJTs. For MOSFETs, there's CGD, C gate to source, and then body, drain to body. So these are the three key parameters we'll keep in mind for our discussions. Okay? So once we have this outlined, next thing we're going to do is, of course, to give you a more general outline as to how does one approach this type of problem. So we start with the common source, the first one. I believe we already go through one example, so I'm just going to give you a general analysis guidelines. So this, you can actually see this in the textbook as well. So basically, if you consider a common source stage on the left, let's make it a more general case. So this is a common source on the left. And then I have basically two resistance. The impacts are resistance and at this input terminal, X terminal and Y terminal. We look at two terminals, that's X and Y. So if I label this input terminal as X, output terminal as Y, this can be, we can also construct a common source, common emitter, sorry, into the bipolar version. So follow the same topology, it's just a different transistor. Either you use a MOSFET or you use a bipolar. The structure is the same, R load, RS. So you basically, at the input terminal, there is a source resistance. And at the output terminal, there is a loading resistance. So you look at the input terminal, which is Vx, output terminal as Vy. So this will be my input. Y point is the output. It's the same for this is V out. Okay? So for these two stages, you need to think about in considering high frequency analysis, we need to inject our parasitic capacitance. As I said, these are the three capacitance we mostly concern about. So the input terminal, there's CGS. At the feed forward, there's a feed forward in this type of architecture, CGD. And then finally, at the loading terminal, there's CG, the space, I didn't keep enough space. That's fine. Let me try to move this over. Is it M1? So this will be CDB. That's the junction capacitance from drain to body. Okay? And we can also do this for bipolar. For bipolar, the input terminal, you see a C pi. And the feed forward is C mu. And the loading capacitance, based on the parasitic structure, this is CCS. CCS stands for collector to substrate capacitance. So once we have this, we can construct a equivalent circuit. So the equivalent circuit, both circuits can be rearranged with a Thevenin equivalent, RS. So you do a Thevenin equivalent at the input terminal. So this will be V Thevenin. R Thevenin, sorry, R Thevenin. And then we have the input port, which has an input capacitance. Input terminal has an input capacitance. There's a bridging capacitance, bridging between CXY. So depending on whether it's a MOSFET or a bipolar, CXY can be C pi, C mu, or CGD. And then the small signal equivalent circuit, GM VX. VX stands for this terminal. And then we'll then connect it to a output capacitance C out, and then to C load. All load. So this will be the equivalent, small signal equivalent model. In general, for both, we can generalize in terms of this equivalent circuit. And then we want to, because there's a feed-forward capacitance, so we want to do Miller approximation. You separate CXY between the two input and output terminal. So let me label this more clearly. This is the X node. This is true for both circuits. So your output will then turn into, this can be further generalized as, I'm going to explain all these terms. V Thevenin. And then my input will then be it will be 2 capacitance C int plus Cx. And then Miller separating these two, GMVX. And then there will be CY plus C out plus R load. So your circuit can be generalized, further generalized as this. So once we have this, then you can find this pole, node X and node Y. This is the input node. This is the output node. So for the input node, it will introduce omega P in. This is based on node X. This can be simply this resistance times the overall capacitance. So RC, which is R Thevenin, C, okay, over 1. And at the output terminal, which is coming from node Y, based on node Y, its equivalent resistance is, you don't see this is infinite, ideal current source. So you only see R load. The RC time constant, the C is output plus CY over 1. Okay? So this is the overall generalization, but then you need to know all your general parameters. So let's give the general parameters here. For each one of this, you can separate into common. So for common emitter against common source stage, there's various parameters we need to find out. Sorry, I forgot to say this. So in general, we know that Cx, Miller approximation tells us that Cx equals to the overall gain 1 plus GM R load CXY. And CY equals to 1 plus 1 over GM R load CXY. So this is simply, by Miller approximation, you could get Cx and Cy respectively. So within this composition, you need to know, in common emitter stage, because there is an input resistance, so there's a voltage dividing factor, therefore you need to consider Thevenin equivalent. So V Thevenin, the parameter V Thevenin, let me give a better table. So we're going to set all the parameters straight. So the unknown parameters are V Thevenin for CE stage and CS stage, respectively. And then we need to know R Thevenin in order to solve for omega px or omega p in. And then we need to know what CXY is in order to get Cx and Cy respectively. And then what are the corresponding C in and C out. Okay? So for common emitter, that's the bipolar version because there's a voltage dividing factor, so this will be R pi, Rs. It's voltage dividing Vn. And your R Thevenin will be this two in parallel, Rs in parallel R pi. So this is when I see this, how do I see this input resistance, how do I get an equivalent, Thevenin equivalent model out of that? I'm sorry. I misplaced this. So this is Rs in parallel R pi. So this is for common emitter stage. And we know that the feed forward in this bipolar architecture is C mu. And its input capacitance C pi, and loading capacitance is CCS, which is, as I said, collector to substrate capacitance. Okay? So for the common source stage, because your input resistance is infinite, so you assume that R pi is infinite, therefore you get Vin. Because R pi is infinite, so you get RS. Right? Because there's no R pi is infinite in MOSFET version. And this is CGD. This is CGS. Input, output. Okay? So once you have this, you can substitute in here to get all the input and output resistance accordingly. And an input node, input pole and output pole accordingly through this Miller approximation to get the overall capacitance, including its input capacitance, typically CGS or CGD, and then your feed-forward capacitance, Miller effect after Miller amplification effect. Okay? So this is for high-frequency analysis. And the other thing we often discuss is what we call the input. The other thing typically is being considered is called the input impedance of the circuit. C, E, and CS. What does this mean? This means that if I have a, remember, aside from knowing the gain, we want to know what is the corresponding impedance if I'm looking in from here. That's called the input impedance by considering also the capacitive component. So this, the bipolar version, the MOSFET version will look something like this. I'm sorry. I'm going to draw the MOSFET version as M1. And then, so what we want to do is to look at Z in these two cases. So we know that for if you're looking at input resistance, bipolar doesn't have any. Bipolar is R pi mostly. And then if you don't consider parasitic component, but parasitic resistance capacitance components. But now if we include that, there will be, again, C pi, C mu. If you look in from the input terminal, these are the two main components. So based on Miller approximation, Z in should be R pi. That's the DC leakage current you have, this R pi still. And in parallel to the two capacitance, which is J omega C pi plus C mu. I should say Cx over 1. Or if I rewrite this as C pi in parallel J omega C pi. This is the Miller capacitance plus C mu is being amplified by a factor of GM R load. Okay? So typically you would then experience a fairly high, or I should say low impedance at higher frequencies, mainly coming from this Miller amplification factor. This would contribute to an effectively large capacitance. As I said, the basic concept of Miller approximation is because the terminal is moving in the opposite direction, therefore this node will be slowed down because it takes a lot more charge for this node to move. So you would then see effectively low impedance. Low impedance meaning that it needs a lot of charging current. So we can do that for the MOSFET versions. For the MOSFET version, remember in our previous analysis, if you consider frequency as 0, this will be R pi. At frequency as 0, you don't actually see any, so it's infinite. So Z in this case will simply be, you only have the charging component, so it will be J omega. The effective capacitance, as I said, it's CGS plus CX, right, at this particular node. Let's highlight the capacitance. So the input terminal, there's CGS. The output terminal is CGD. You only, from the input terminal, you only see the effect of these two capacitance. And this can be rewritten as 1 J omega. Let me use the green to be consistent. 1 over J omega CGS plus Miller amplification factor GMR load, the gain of the stage times C GD. Okay? I need another bracket. Okay? So this is the same thing as I said. To go back and check when frequency approaching 0, Z in equals to infinite. In this case, in the bipolar case, when omega approaching 0, this one is infinite, therefore Z in is R pi. So you only have the base current. This is the DC base current effect. Okay? So the impedance would then describe base current in parallel with the charging current of parasitic capacitance. So these are to govern the charging current. So for MOSFET, there's only describing the charging current. I should say AC charging current to pull your baggage, to pull your parasitic capacitance, CGS, CGD. But this is not actually the I should say CX, being amplified, after being amplified. The charging current required to pull up this particular node, that would determine your impedance, okay? Okay, once we have that understanding, let me go through a simple example before we go to the low frequency part. So let's give an example of a common source stage. We have a common source stage with a PMOS load. The problem with, if you have a transistor load, the loading itself will then introduce certain amount of capacitance as well, so that needs to be included. So let's visit this example. So let's say instead of having a resistive load, I'm using a PMOS load. So this will be, M2 will be my PMOS load. M1 is the common source amplifier. As I said, you need to be able to identify what is the purpose of each one of the transistors. So let's say this is my input terminal. This is my output terminal. So you need to find the expression for omega p. So find the expression. The question is to find the the expression for omega p in input terminal and omega p out. Okay? So first of all, we need to, before we do that, we need to understand what are the parasitic capacitance needs to be considered. So let's add them as we go. So there's, again, from the gate terminal to source, CGS. And there's this feed-forward, which is CGD. And then at this terminal, at the drain terminal, there's drain to body. And because we have two transistors, I'm going to label it as M1. It may be of the different size, therefore its parasitic capacitance can be different. So at this drain terminal, this is also a drain terminal. So if you're looking at the N2 drain terminal, there should be a CDB, drain to body 2. Okay? So based on our guideline, let's first fill in all the parameters. First of all, what is the corresponding CXY? So in this case, CXY is CGD. And therefore, CX is 1 plus GM. Instead of RD, it should be the gain, GM1, RO1 in parallel RO2. That's supposed to be its DC gain. That will be the gain times CGD. So you get CX, CXY, CX. And CY, of course, is the same based on 1 plus GM1, RO1, RO2 over 1 CGD. So once we know our CX and CY, we should be able to get this, your input terminal, because in this case, R Thevenin is RS. Therefore, I should be able to get VP in equals to RS. C in, again, let me highlight it here. Input terminal, the capacitance should be only CGS1. And the output terminal, instead of having CDB1, I'm adding another PMOS from the top. Therefore, you need to add CDB2. Okay? So that's two parasitic capacitance at the loading terminal. So this will simply be my C in, which is CGS1, plus this term, 1 plus GM1. Let me finish it. RO1 in parallel RO2, that's the gain, times CGD. And then I need a largest bracket at the external. Okay, over 1. Once again, this is the input capacitance. This is CX by Miller approximation. And then your resistance is RS at the input terminal. And we can also do this for the output terminal and use a different color just to highlight the difference. So for the output terminal, VP out will be depending on its effective resistance at this R out, which is on RO1 in parallel RO2 times its capacitive component. Capacitive component including R out, which is let me give the large bracket. So which is CDB1 plus CDB2, okay, plus CY. I don't have space for this, so let me just give it this. Okay, so this is the resistive RC component over 1, where, let me put CY here. This is CY. So you simply put this into this equation, and you should be able to get input and output poles, respectively. Okay? And just to give a general comment, in this type of circuit, mainly what happened is that you would then have, because of Miller amplification effect, if your gain is not too small, typically omega p in will be the dominant pole. In most cases, meaning that omega p in is typically smaller than omega p out. In most cases, because of the amplification factor, the resistive component, even though typically if you have a source, voltage source, RS can be fairly small. But if you consider in a circuit, in an integrated circuit, this can be the output resistance of a previous stage. So that resistance are typically in the same order of magnitude. When capacitance is much, much higher, then it would then create a dominant pole, which would then affect your corner frequency. So this would then give you the omega minus 3 dB. Will be very close to describe the corner or bandwidth of the overall circuit. Okay? Okay, so this is the high frequency part. Let's talk a little bit on what are the impact of external capacitance. I'm going to just quickly address what are the typical response of a low frequency response. What are the low frequency response analysis? As I said, as a result of coupling capacitance and maybe bypass capacitance. So let me give an example. So typically what we have for a, remember if you're constructing your if we're constructing a common source stage, to set the DC bias, you typically need a resistive network to set the bias. And to further stabilize it, what is typically being done is that you add a source generation. So let's say if I have a circuit with source generation to further stabilize my DC biasing, and this is M1. And then because this is R1, R2 is to set the DC, R1, R2 is used to set ID1, so that my input may not be at this level. So the capacitance being the external, as I said, the external capacitance being added here is the coupling capacitance, CC, so that it's connected to an input. So we can then establish a DC, meaning that this DC level of the input level can be independent from this biasing DC level here, VG. And then this is called the coupling capacitance. And the other thing, other component is called the bypass capacitance. So there's two capacitance as let me write it down. CC stands for the coupling, is to make sure that your DC level does not have to match. And CB stands for the bypass cap. Okay? So I will explain why. So in low frequency response, what it means is that you want to see what are when frequency is at its high level, you assume. So this circuit, these CC and CB are large, so that when frequency is high enough, you don't actually see them. So you assume CC and CB are short. At high frequency, or typically at your operation frequency. So the circuit will simply become, your small signal circuit will simply become equivalent to that. So you will see that it will return back to, even though you have degeneration, but at high frequency it will short it. So once it's shorted, this is short, so you don't actually see the effect of R1, R2. So then it will just simply become whatever we have already discussed in our previous analysis. And then you enter into high frequency domain analysis without considering all this capacitance, external capacitance. But what is the effect if you want to look at what are the bandwidth or the limitation on how low the frequency can go, your signal bandwidth at the lower regime? So to do that, we could actually get the transfer function of the circuit. So to do that, you find out the x note. So if you want to get Vx as a function of Vn, this can be, so you simply see the input resistance is R1 in parallel R2. So this is a high pass configuration. So high pass configuration tells us is R1 in parallel R2, R1 in parallel R2 plus, so it's a voltage divider CC over 1. Okay? So this would then introduce, a omega 0. This equation, let me rewrite this. You can rearrange the circuit as J omega CC R1 in parallel R2, 1 plus J omega CC R1 R2. So this part will give us a zero frequency, and then you have a pole at CC R1 in parallel R2. Okay? So we're going to do the Bode plot later once we have all this layout. And for the second part, you have V out as a function of Vx. So you consider a degenerated circuit. So its gain should be minus GMRD. Okay? So the bottom should be 1 plus GM. Instead of RS, you will then have a CB in parallel. Therefore, RS in parallel J omega CB over 1. Okay? So this just follow degenerate equation. So after some rearrangement, we're going to get a minus GMRD. You get a low frequency, high frequency equivalent gain, which is GMRD over 1 over GMRS. And then there's this frequency component, 1 plus j omega z2. I should say there's, because we have two zeros in this equation, in this circuit, I should say, omega p2. Okay? So the overall transfer function should be, the overall transfer function of the circuit, VL, Vn, should be minus Gm. Let me get the DC term. 1 plus GMRS. And then we have the zero term, which is j omega cc R1 in parallel R2. 1 plus j omega cc R1 in parallel R2. Plus 1 plus j omega z2. I should use j omega z a p2. This can be rewritten as, let me rewrite this. 1 plus j omega p1. Okay? So once this is given, we just simply need to know the corner frequency, the poles. So as I said, omega p1 is being set by coupling capacitance. And omega z2 is determined by the bypass capacitance. And omega p2, let me just write down all the terms and explain what it means. Okay? So once we have this, typically we have omega p1. It should be much, much smaller than omega z2 and omega p2. And we know that the zero is actually in front of the poles. Z2 is at a low frequency because this is 1 plus GMRS times larger. So this will be omega p2. So to do the Bode plot, you will then know the overall, if I want to draw the circuit, overall transfer function. There's a low frequency regime which will be limited by CC and CB. So I'm just going to label omega p1. There's omega z2, and there's omega p. And then in a very, very long distance away, there will be our omega p in, which is the high frequency component, and then omega p out. Okay? So a very high regime, these are parasitic dominated, and these are coupling or external capacitance dominated. So let's do the overall Bode plot. The overall gain, I should say the overall voltage gain. Voltage gain is a function of frequency as defined by VL. So we know that when your frequency is at fairly high, I should say, let me first find out the high frequency at this regime when, let's do omega, when omega is much, much larger than, omega p2. much, much larger than omega P2, but still smaller than this parasitic component. Let me just say VP1. So at very high frequency, what happened is that this term, this is a high pass filter, so this term will simply be 1. So if I separate them, this term, the magnitude of this term, so your voltage gain, I should say, will become minus GMRD, 1 plus GMRS. So this term, the magnitude of this, the high pass filter is 1. And this will simply be square root of 1 plus omega z squared, 1 plus z2, omega p2 squared. So when this frequency is much larger than omega p2, you don't see the ones. So this term will simply, because it's absolute value, so your overall gain will simply be GMRD 1 plus GMRS. If you don't see the 1, it will simply be omega P2, omega Z2. The ratio between the two is GMRS. So this and this cancel each other. You get GMRD. So this is the target. We want it, when it's operated in the desired frequency bandwidth, the gain should be at, when it passes, before it hits the high frequency, it should be GMRD. Let me use a different color. Yellow. Okay, so this is our target design, which we have been discussed before, without any frequency impact from either the input side or the output side. It should be at this. And then once it hit a pole, it should drop 3 dB, 20 dB, and then this we already discussed. This is minus 20 dB. This is minus. The slope can be highlighted once you hit 2 poles. So at high frequency domain, we already know what happens. At low frequency is slightly more complicated. So remember, we already have a 0. So once we have this point aligned, the next thing we need to think about is that what is the center point? So the center point is when, let me use the equation. See if I get a space. So first of all, we know that there's a 0 at 0 frequency. So it started with, I'm just going to roughly give a level. So what happened is that you would then start with a rise of 20 dB per decade, plus 20 because I have a 0 at 0 frequency. And then once it hits a pole, 20 minus 20, so it should flat out. And then it will then rise again. My slope is not high enough. So make sure my slope is high enough. So we'll reach this level, flat, and then reach another 0 and then rise at a 20. Okay? So this is the effect of the bypass capacitance. We'll see that this is plus 20 again. So the next thing in this plot is that you need to find out what is this flat level. What is this level at this a short flat stage between omega p, between omega p1 and omega z2. So once it passes omega p1, once again we know that the gain of this is still 1. But when it's lower than omega z 2, what happens is that our transfer function, let me write this. So if you want to look at the range when your frequency is higher than omega p1, but smaller than omega z 2. We go back to the equation. So the overall gain magnitude should be Gm Rd 1 plus Gm Rs. And this term, which is Vx, let me just use this, Vn. This term, because it's already past omega p1, so we know that it's approximately 1. And the other term is 1 plus omega z2 squared, 1 plus omega p2 squared. Okay? So because the frequency is much smaller, this means that in this case, when I ignore this and that, so this will be approximately 1 as well. So this is 1, therefore your gain will simply be Gm Rd 1 plus Gm Rs. So this simply tells us that this flat region, within this flat region, this should be, let me use a bright color. We should be able to identify at this particular point is GMRD 1 plus GMRs. Okay? So this is before bypass kick in. At this particular frequency, because the bypass, your impedance is still competing between RS and RB and CB. So when RS still dominates, you will see the effect of RS, meaning that you see the effect of degeneration. But once frequency exceeded to a certain level where CB dominated will view as a short, then you will see that it rises up, and then your overall gain will look like the equivalent circuit on the right-hand top. Okay? So that's the overall frequency response you should be able to understand or analyze for a common source and common base stage. Okay? Well, so let's give a general overview on a common gate and common base stage. So we're going to first do the low frequency part and then look at the high frequency part. So first at low frequency operation. So as I said, these are typically determined by coupling capacitance. So let's assume that I have a common base circuit, looks something like this. Remember, for a common base structure, I have my input coming in. This will be a fixed bias. The base will be at a fixed bias. The input will come in. Let's say I have a certain current source load, a current source biasing component. So once we have this current source biasing component, so the input may come in through a coupling capacitance Ci, and my source, I'm just going to give a Ri. And this will be my input source, signal source, coming in at the emitter terminal. And the output is connected at the output terminal VL. Okay? So once this is the case, then you can actually redraw the equivalent circuit as to your input is like this. you would then still have a high-pass component, because anytime you have capacitance in parallel to your signal path, not in parallel, but in between the signal path, bridging the signal path, this will then lead to a high-pass component. And then this part, we can use the two-port model. Of a common base stage. So remember, the input resistance of this is simply very close to dominated by 1 over GM. That's the input resistance. And then I have a voltage gain, V1. This is V1. So you go back to the input resistance. Of course, there's an R-pi component. You can ignore that. So I'm simply using Rn as GM. And this is the voltage gain. And connected to RC VL. OK? So we know that in this model, let me see. In this model, you have the two-pole model. They come in with 3 parameters. Rn, which is 1 over GM. I should say AV voltage gain is GMRC. And your output resistance is just RC. So we simply use this model to construct our transfer function as VL in the low frequency analysis of the transfer function. So VL as a function of Vn can be rewritten as A0. That's the voltage gain. One plus J omega Z. There's a 0, and there's a pole. So based on this model, this dividing capacitive component can give us the relationship between V1 and Vn. And that would introduce omega 0. Where in here, A0, let me give the parameter. So once you construct this transfer function, A0 is GMRC 1 plus GMRS. Because of the voltage dividing component from the front, that will introduce the relationship of Vn and V1. The DC component is 1 over 1 plus GMRS, and then times the overall gain. That's the AV. Okay? So then we could get the, let me label it as 1. So from here, we could actually construct our transfer Bode plot. So the Bode plot of this, let me construct it here. So we already know that based on this transfer function, we know that at high frequency, this is a high-pass filter, so let me highlight this. Omega Z1 is at 0 because there's only the high-pass component is bridging input signal path. And omega P1 is determined by RICI over 1. So this is very similar to what we see for a coupling capacitance. It will start at a rate of increasing at a rate of plus 20 dB per decade. And then it will flatten out at omega P1, which is 1 over RICI. That's a high-pass component. And we know that at this turning point, the gain should be GMRC, 1 plus GMRS. Okay? So that's just when you have source resistance, that's the overall gain that we obtain. So let's look at the high frequency side. So this is the low frequency side. When we analyze the high frequency side, what are the components that affect the high frequency path? So if you think about it, in high frequency component, let me redraw this plot. This will be your RC, VCC. Q1. So we're going to include our, so in high frequency discussion, what happens is that you assume that your capacitance CI, in high frequency discussion, we assume CI as short. So your equivalent circuit will be something like this, RS Vin. Okay? So let's look at its capacitive component. So remember, this is AC ground for small signal analysis. So what you see is there's a capacitance C pi. It's connected to ground. And there's another capacitance C mu. It's also connected to ground. So your input terminal, let's say if this is the input terminal, X node. And then I have a output terminal at Y node. So omega px, let's use omega px. So you look at the capacitive component, we only have, let me emphasize again. Both C pi and C mu are grounded in one side, at one side. That means that there's no feed-forward capacitance. So no Miller effect. This is very different from our previous analysis when you have common source and common emitter architecture where you have capacitance bridging the input and output terminal. In this case, there's no capacitance between X and Y. So there's no bridging or feed-forward capacitance. So that will make our life much easier. So you only need to think about omega, let's say omega P in, which is based on X node. So would be determined by the resistive components at the input terminal, which will be RS in parallel 1 over GM. And then at this particular terminal, what you have is simply C pi, right? At the input terminal over 1. And at output terminal, it will be RC times its resistance is C mu. If you want to add CCS, that's fine. So if you need to consider this node, there will be another loading capacitance CCS over 1. Okay? So this will then make these two capacitance, once again, there's no amplification effect, so this parasitic capacitance of C pi may be slightly higher, but we know that its input resistance is 1 over GM is very small. Therefore, if 1 over GM dominates, this will then be a very high frequency pole. This will also be a very high frequency pole. So that's when you have, it will be fairly close to, let me write this down. So if you consider omega P in, let's say RS is larger than 1 over GM, if that's the case, because if you're or even at a comparable level for impedance matching case, or you want to have a low input resistance. That's the basic idea of having a common gate stage. So let's say if this is the case, then omega p in will be approximated by 1 over gm c pi over 1. So this is gm c pi. If you look at this, this is almost ft. This is even higher than the bandwidth. That is to say that the poles, omega p in, is at a very high frequency, meaning that you have a wide bandwidth. So in this case, typically you would then have omega p out maybe slightly smaller than omega p in. But both of them will be at very high frequency domain. That is why typically one of the benefits or one of the features typically mentioned for having a common gate or common base stage is that it will then deliver a much higher frequency circuit, typically to the limit, high frequency or bandwidth circuit. Because the main reason is because it does not subject to known Miller amplification. So both your capacitance is whatever it is. Whatever parasitic capacitance would then dominate, that would then lead to your ultimate circuit limit. That's your FT. So these are the bandwidth of the circuit would naturally approach the intrinsic frequency, intrinsic transit frequency, or intrinsic bandwidth. Okay? We could also do this on we could do this analysis on a common gate amplifier. I'm going to use an example. So example. So let's only look at the high frequency part. Example of a common gate stage at high frequency. So we only want to find out these omega. So these are very wide, as I said, it will go all the way. And then at very high frequency, you will hit maybe omega p out first. And then omega p in. Might be close by. So overall response will be very similar to that. Okay? So this is the mid-band. Operation region. Okay? Your lower frequency is limited by coupling capacitance. Lower boundary, higher frequency is limited by parasitic. Okay? So let's look at an example so you get a sense as to what needs to be done to approach this type of problem. So let's use a common gate stage. So I'm going to use a slightly complicated loading design. So let's say if the circuit looks something like this and comes in through an RS in. I have M1 and this is at a fixed bias, so common gate. And input coming in as source, output taking out at drain. Okay? Instead of having a I'm using a loading, which is somewhat tricky. It's a PMOS, but with a diode connected load, so that I can get like a linear gain, that type of architecture. So if this is the case, let's think about what are the parasitic capacitance needs to be considered if this is being connected this way. So if you look at these capacitance, there will be CGS1. There will be GD1. Okay? I'm using this die connector just to amplify as to what are the capacitance you need to consider in this case. So this is being shorted all the way to here, so there will be another additional loading of CGS2. Okay? And because this is connected to the drain, so you need to consider another CDB2. And for the drain of M1, there's CDB1. Okay? So if you look at node X, all the capacitance at the input terminal, this is node X, this is node Y. So for the input terminal, as we have already discussed, for all the capacitors connected to node X, CX, will simply be this one, CGS1. And because the source might not be connected to body, but if you want to include that, there may be, this is the source terminal because source and body are not tight. So you might also include CSB. Source and body, there may be additional capacitance. So for the X node, the overall capacitance will be CGS, CSB. That's based on M1, that's the amplifying capacitance. And for the diode connected load, this is the, let me highlight, M1 is constructing the common gate stage. The main amplifier for common gate stage, M2, is to construct the, we call it diode connected. It's a diode connected load where you have drain and gate shorted. That's what we call, referred to as a diode connected architecture. So at node, so this is correspond to node X. If we look at node Y, what happened is that you will then, at node Y, the overall capacitance will simply be CGD1, this one. Let me highlight it. So for node X, this is 1, 2. And from X to ground, this is ground. This is AC ground, remember? So for node Y, let's highlight. There's 1 capacitance, 2, 3, and 4. So it's actually 4 capacitance, CGD1 plus CGS2 plus CDB1 plus CDB2. This CGS2 is simply because of the diode connected. If you did not use the diode connected architecture, you only see CDB1. Okay, that's based on node X. Node. Okay. So let's give some numbers so you can get to the frequency. So as I said, for this case, your omega P in, let's highlight again, omega P in will be Cx times Rs in parallel 1 over Gm over 1. Your omega P out will simply be all the capacitance looking at the output terminal times RC, RD. In this case, it will be output resistance, which is R01 in parallel R02. Okay? So let's give some number and get a sense as to what are the typical bandwidth of such a circuit. I should say no Miller. Okay? Let me use this half page to finish our discussion on this common gate example with die-connected low. So let's give the parameters. Let's say if RS is 200 ohm, and I have a GM 1 equals to GM2 at 6.7 milliamp per volt. And then we have these, both transistors has the same CGS. CGS equals to 250 femtofarad. CGD, they're the same in size, 80. And I have CDB, because these are symmetric devices, we're assuming that they're all the same. Okay, so once we have this, we should be able to find, so once we have this, ask you to find its poles, 1 omega p in and out. And determine which one is the dominant pole. Dominant pole. So which one is smaller? Dominant pole simply means that the lower frequency one, either it's in the input terminal or at the output terminal. So first of all, we need to figure out what Cx is. So based on this equation, we know that CGS 250 plus CSB, which is 100, that will give us 350 femtofarad. And at the Y terminal, there's CGD, that's 80, plus CGS, that's 250, plus another 200, because there's two of them, two drain to body capacitance. So that's. So once we have these parasitic capacitance outlined, we should be able to find omega Pn. So before we do that, we need this. We need Rs in parallel, 1 over Gm. So since we already know the Gm, so this will give us about 85 ohm. So you simply insert a number to find the input resistance, the resistance at the input terminal. So this will give us as to 250 times 85. That's femto, that's ohm. And that will give us about 34 giga radius. This is very high frequency. As I said, very close to FT because this is very high GM over, it's GM over C pi. Omega P out, based on these numbers, because it has a slightly higher capacitance low because of die-connected structure, and then we have this output resistance. Okay, the output resistance is actually 1 over Gm. I forgot to highlight at this point because I made a mistake here. In this case, because I have a diode-connected structure, so therefore this may not be RO2. I should rewrite this. This is CY times R out. And at the output terminal, R out should be RO1. Because this is diode connected, remember if you go back to C diode connected architecture, it should be 1 over GM2. I forgot to include that. So this will be approximately CY GM2. Okay? So omega P out in this case will be GM2. That will give us a frequency of 12.5 gigaradius. Okay? So both are at a fairly high frequency, and omega P out is slightly higher mainly because it's not because of any amplification factor, it's simply because of the diode connected structure make the loading capacitance CY slightly higher. That is why you see that becoming the dominant component. Okay? So just to give you an exercise, what you need to know about common gate stage, I want to sort of summarize once again. On common gate stage or common base stage, the key feature is that these parasitic capacitance are none of them having the feed forward. There's no CXY. There's no feeding forward capacitance. Therefore, there's no amplification effect. Without this amplification effect, its frequency, I should say its bandwidth will typically limit by its transit, very close to transit frequency. So you can see that its corner frequency or dominant pole is very close to its corner frequency. So this will be determined by omega P out. The dominant pole, in this case, will be omega P out. And omega P out is at GM2, a CY. So typically what it means is that GM2 typically means that it's actually a low impedance node, meaning that if you have 1 over GM, meaning that the resistance itself is very low, meaning that it can supply high enough current so that at this particular node, when the capacitance is very small, then the frequency can be extended to fairly wide bandwidth circuits. So common gate stage is typically referred to as a good wide bandgap architecture, even with the parasitic effects. Okay? So we still have 15 minutes. Let's sort of start on the last discussion on the frequency response of the follower circuits. If we can finish up this, this part, then I'm probably going to leave Thursday for discussion. So we're going to discuss that, the plan later. So frequency. We're going to talk about frequency response of follower circuits. It's in the discussion of follower circuits, it's relatively complicated, so we want to make our example simplified just to get the main point of what it looks like. So if you think about your follower circuit, let's just use a emitter follower as an example. Let's say I have a current source biasing. So in a follower circuit, as we typically understand, it's being used to drive a low resistant loading, like our speaker, remember, a very low resistance level or high capacitive level, meaning that it needs to provide high current. So if this is the case, its external circuit is simply connected to provide the C load. So if this is V out, it's V in. And then I have this transistor. So let's draw our parasitic capacitance. I have this. If we first look at this architecture, first of all, it will have some feed-forward capacitance because this is the input terminal. So you have C pi as the feed-forward. But because, remember, I have a follower circuit, meaning that, and then the second thing is that C mu, and C mu's are grounded at collector terminal, at the collector terminal. Right? This is the AC ground. So you, instead of having a feed-forward as C mu, you now have C mu as a sort of an input loading capacitance. And then the last thing you observe is that if you think about the voltage gain, VL, remember it's a follower circuit, so this is larger than 1. Not large, it's positive, I should say. Is smaller than 1 and positive. That's what typically is. It's less than 1 and it's positive. So that it means that the effect of Miller effect would then have a attenuation factor, meaning that I have someone helping me pulling up the opposite terminal, meaning that I would then experience C pi. Well, the effective, I should say, the effective Cx is reduced. Okay, so we're going to talk about that when we talk about input impedance and output impedance. So before we actually enter the discussion of impedance, let's spend a little time on discussing its transfer characteristic of this particular circuit. So the way to do this is to construct our small signal model. So simply what happens is that you will consider the case when it's driving. So remember, you have C mu become an input capacitance because it's grounded in the other side. And then I have an RC network. This will be my R. This will be my C. Is connected to, so we ignore these R pi effect, R out effect, and this output is grounded. And then I'm driving a load of loading capacitance. It can be external because that's what a follower circuit typically do, is to drive a loading, typically large loading resistance. So this can be viewed as an external capacitance being added. Okay? So let's highlight the nodes. There's node X, and there's node Y at the output. So if you think about analyzing at node Y, what are the current that's coming down at node Y? So the current coming down is G and V pi. The current going down here, let's say I load. So if I'm drawing the total current flowing down to the loading capacitance, if I'm trying to find this, so what are the components? There's one of the, of course, the collector current mostly. That's the main component. And then there's V pi. This is V pi. There's V pi R pi. That's the base current. And then there's j omega C pi V pi. So this branch and that branch. There's 3 branches coming together to provide the load current, the loading current. We're ignoring this because this is collector current, this is base current. We know that collector current is much larger than the base current. So that your overall output voltage, VL, should be the current I load times impedance of this C load. Okay, you simply insert that in, and then we get this as, this is V out. And then from simply insert that in, it will be GM V pi 1 plus j omega C pi V pi divided by j omega C load. So we can get the relationship between V pi and VL. So we get V pi, and I said approximately it's j omega C load GM plus j omega C pi times VL. So we get the relationship between VL and V pi. That's the first thing. And then what is Vn? That's that we know that VL and V pi. And Vn is actually V pi plus VL. So this would then give us using this relationship, we get Vn as a function of V pi as well. It's 1 plus GM. It's somewhat tedious, but we're going to get to the results so you get a sense as to what actually means by this. Once we get this relationship, we can get our transfer function, which is VL as a function of Vn. So we get VL as a function of Vn. So that will be my transfer function. And after rearranging these, you get a result as 1 plus j omega z, 1 plus j omega p. So in this circuit, you get a 0 and a pole. And let me highlight where the zeros and poles are. So as we already find out that this transfer function governed by a 0 and a pole based on this equation where it's 0 is at close to corner a transit frequency. Its pole is C pi plus C load, depending on the load. Okay? So this is simply by constructing the small signal equivalent circuit and get the overall transfer function. So if I want to get the absolute value of this, this will simply be square root 1 plus omega p squared, 1 plus omega z squared. Okay? So how does one construct its Bode plot? You look at extreme cases. So first of all, in this type of, when you want to draw the Bode plots, what we typically do is that we look at extreme terminals. You want to see when frequency is very, very low and when frequency is very high. So let's just label our omega. These both frequencies are actually very high. So it's omega p is actually at a lower frequency, and then you have omega z. We know that the relationship between omega p and omega z, omega p should be smaller, right? Because capacitor is larger. So based on this equation, we know that omega p must be smaller than omega z. The other thing is that you look for boundaries before you do the plot. So let's start with the boundary of very low frequency. So at 0 frequency, first of all, when frequency is very low, approaching 0, what happens is that you're actually having a gain, voltage gain of 1, right? Because you don't see this. When frequency is very low, 1 dominates. Or I should say, this means that when omega is smaller than omega p, right? So we know that it starts at 0 dB, a gain of. Why does it experience a gain of 1? If you look at the circuit, when frequency is very low, the impedance is infinite. So you have a follower with an impedance of infinite. That means that again approaching 1, right? When Z out or R, I should say R out is infinite, then your follower circuit will then experience a gain of 1 at very low frequency. And once it hit the pole, we know that once it hit the pole, that's just not, it will start dropping at a rate of 20 dB per decade. So as I said, when it drops at a rate of 20 dB per decade, the amount of drop is the same as this 2. And then it hit the 0. Following, let's go back to Bode rules. You started flat at 0, and then when it hit omega p, it will start dropping at a minus 20 dB per decade rate. Once it starts dropping, and then it hit another 0, so it flattens out again. So minus 20 plus 20 becomes 0 again. So it will become flat again. So in this plot, I want to know what this is. So when it becomes flat, what is its level? So this is, if this gain is 1, let me use 1 instead. So this is my gain, VL, Vin, or voltage gain. The magnitude of the voltage gain starts as 1, and then it drops at 20 dB per decade. Remember, when it drops at this rate, what it means is that the ratio between these 2 points, this and here, the ratio between these 2 points is the same as ratio between these 2 points. Okay? So let's say this is x. So 1 over x is the same as omega z over omega p. It's a squared